Okay, so what we're going to do today is get into a little bit more of the nitty-gritty detail of formal logic, starting with negations of statements, which are, this is a great example of how formal logic is at both, somewhat intuitive, I think more so than, say, algebra, but that can be deceptive because there are little details that can be confusing, okay, that come up. So we want to be very careful and deliberate about what we do. However, the intuition that you have about things, we want to build off of. It's typically going to be the right direction to go. Okay, so let's just go ahead and dive in and look at something called the negation of a statement. Okay, so when we're working with algebra and we say want to add numbers, we have an opposite operation, subtraction, okay? And that also gives us an opposite number, relative to addition, right? And we get a negative, okay? And we get the same thing with multiplication. We get an operation that'll undo multiplication division, and we get sort of an opposite in a sense of multiplication, and that would be like the reciprocal, right? 1 over that number, okay? So in logic, when we're combining things, we're looking at truth values, and we have something called the negation, okay, which is like the opposite of a statement. Okay, so when we're looking at a simple statement, it has an opposite. Okay, that opposite is false when the original statement is true, and that negation is true when the original statement is false. Okay, so it's important that when we think of the negation, it's always the opposite, not just sometimes the opposite. Okay, so let's look at some examples. Consider the simple statement, it is raining outside. Okay, an easy way to negate that statement would be to say it is not raining outside. Okay, then if it's raining outside is true, then the statement it is not raining outside would be false. And vice versa, if it is raining outside is false, that means it's not raining outside. So the statement it is not raining outside would be true. Okay, so throwing a not in there is an effective way to make a negation, right? Usually we can negate a statement by adding the word not somewhere. Sometimes, we might want to be a little bit more careful or add a little bit more language around it. Okay, so when we're looking at more complex statements, okay, or somewhere where the not might be confusing, okay, we want to make sure that we're talking about like the whole sentence and instead of just a single part, we could use something like, it is not the case that. Okay, so for example, I could say, it is not the case that it is raining outside. All right, now we need to be very careful. These statements are not negations of our original statement. It is snowing outside. Okay, so it is raining outside and it is snowing outside are not negations, because if I look out my window right now, it's neither raining nor snowing, so both of those are false. Okay. Okay, and you get some crazy winters where maybe both are true. Maybe it's raining and snowing at the same time. I don't know. Okay, same thing with like, it is raining inside. Okay, that's a strange thing that might happen. Okay, but that seems to be unrelated to what's happening outside. Okay, so these are not negations. They're different. Okay, they might often have a different truth value than your original statement, but they're not guaranteed to always be the opposite truth value. All right, we can symbolize negation when we use a truth table. Now remember, when we're constructing a truth table, we typically abbreviate a sentence or a statement as a single letter, like P. So when we want to represent the negation, we'll use this symbol in front of it, right? This tilde P, which we read as not P, and that has the opposite truth value. So this is what this would look like in a truth table. In a truth table, I would write P, and it has two possible truth values, true and false. So then not P is going to be false when P is true, and true when P is false. Okay. Now, one of the things I want to connect back to, yesterday we said that when I take a simple statement, I have two truth values. If I add another simple statement, I double the number of rows in my truth table. I'll have 4. And here that didn't happen because I didn't add a new simple statement. Not P is not new. I'm taking my simple statement that I had before P and doing something to it. Okay, so I don't have extra simple statements, so I still have the same 2 rows. Okay. When we define simple statements, typically what we want to do to keep things clear is we define them to be positive. Okay, so if I want to symbolize the statement, Carl is not a teacher, I don't want to make, Carol is not a teacher, I don't want to make that my statement P, because that's not a positive statement. That's not saying something that Carol is, that's saying something that she is not. Okay, so what we would do is we would first define the simple statement P, that Carol is a teacher. Okay, then the statement Carol is not a teacher is symbolized as not P. Okay, this is done for clarity because if we allow, anything to be a statement and you just write it as P, then it's very easy to get confused when you negate a statement that has a not in it. Okay, you can do that, it just gets more confusing. So when we use conventions like this, it's to keep things clear. All right, some statements have an opposite that doesn't use the word not. Okay, so we have to be careful that the terms are really opposite. Okay, so for example, if we define P to be the statement the store is open, then not P, we could throw a not in there. We could say that the store is not open, but another way to say that is that the store is closed. Okay, and we have to be careful that those are the only 2 possibilities, that a store is either open or closed, and that those are, opposites of one another. All right. So now let's talk about a way that we can connect statements together. Right? This is called a conjunction. A conjunction is a way to combine 2 statements. So negation is just the opposite, yes. Now we have to be careful. Negation is always the opposite. So we don't need to know whether a statement is true or false to know whether or not something is the negation. Okay, so if I say a true statement, it's not that any statement that's false is the negation. Okay, it's a statement that's always the opposite. Okay, but yes, you can think of a negation as an opposite. Maybe we'll write that here. Okay, so simple statement has an opposite. That opposite is the negation. Okay, and that's sort of what we wrote down here with this truth table, but maybe that's a little bit confusing. Okay, so a conjunction is a little bit different. A negation was taking a statement and saying, all right, we're going to define its opposite. A conjunction is a way to combine 2 statements. Okay, and we'll look at this in a second, but a conjunction is a well, let's see if we can figure out what it is. Okay. We want to combine two statements in a way that requires both of them to be true. Okay. So if I look at the statement, Alice played video games, and the statement Q, Bob read a book. Okay. If I wanted to say that both of these are true, what could I say? Think of an English sentence that would mean Alice played video games is true, and also Bob read a book is true. We could use the word while. Yeah, that would work. Alice played video games while Bob read a book. That would work. Okay. I'm going to throw in the easiest word I can think of here to begin with, and then we'll go back through this in a minute and say, well, what are some of the other words that we could use, right? So while works. Okay. But works. Okay. There's actually quite a few other ones. I know I'm blanking out on what my good examples are. Yet works. Nevertheless. Okay. So these are all words that work as an and statement. Okay. And of course I'll just include and in there. Okay. So sometimes you might refer to a conjunction as just an and statement. Okay. But the conjunction is the more precise word that we have for it. Okay. All right. So again, looking at English, sometimes we can shortcut things a little bit. Okay. If I say that Carol has a cat and Carol has a dog, okay, we could say that Carol has a cat and Carol has a dog. Okay. But more likely what we would say, right, if you were going to communicate this to somebody and actually say something to a real person, and, instead of trying to write up an official homework, you would just say that Carol has a cat and a dog. Okay. And that would mean the same thing, but it's maybe a little bit more concise. Right. So going the other way too, we have to be careful, right? If I see Carol has a cat and a dog, I know that I can break that apart as Carol has a cat as a statement and Carol has a dog as a statement. Okay. Now, one of the things that we like to do in logic, and specifically in symbolic logic, is to take our words and translate them into symbols. Now, this seems confusing at first, but imagine that you were trying to do an algebra problem, okay? So try to imagine solving this equation, and it's not going to be a complicated equation, right? Let's say 2x plus 4 equals 10. Okay, except that you weren't allowed to use any symbols. You had to just write out full sentences, right? So if I had to write out 2 times x plus 4 is equal to 10. Okay. And then I have to write out, okay, subtract 4 from both sides of the equation to get the new equation. Okay. Then writing out this solution, would take like half a page, okay, instead of like, 3 quick lines, right? So when we're solving algebra, writing things out in symbols condenses the information and makes it much easier to work with and manipulate, okay? And the other thing is, when I'm looking at an equation and I want to do something like subtract 4 from both sides, if I write the -4, that's easy to see. When I write the words subtract 4 from both sides, it's not as clear what I'm doing, right? It seems like I can't visualize what's going on, right? I can read the words, but it's not as visually helpful, okay? So when we write things as symbols, okay, although we have to then learn the symbols, right? You have to learn the order of operations, know what all the symbols mean, okay? But once you do that, then it makes things easier. We have the same thing here with logic, okay? We're creating symbols for stuff, and that's going to make it easier to formalize arguments, but it takes a little bit of upfront work where we learn all of the symbols, okay? So when we have a conjunction, an and statement, we use this caret symbol, okay? And it's read as P and Q. So if I were to read this top row of my truth table, I would say I have the statement P, statement Q, and then the complex statement P and Q. Okay. And when we look at the truth values for this statement, first we filled in all the possibilities for P and Q at the same time, right? They can both be true, or just the first one's true, or just the second one's true, or both are false, right? That's all my 4 possibilities. The and statement means that both of them are true. So this and statement is a true statement exactly when P and Q are both true. And the and statement is false when I don't have both of them true, right? If either one of or both of them are false. Okay, so this truth table is sort of telling me some information. It's telling me when is the and statement true. All right. We're going to come back and combine this all together in a minute. But first, I want to get some of our definitions out of the way. So this was a conjunction, right, which is like an and statement. Okay, but and statement isn't really as good a word for it because it could also be a while statement or a but statement or a yet statement. There's a lot of different things that can also be a conjunction. Okay. So now let's look at a disjunction, right? Here we want to combine 2 statements in a way that makes the result true unless both of them are false. Okay. So if I have the statement, Frank does the laundry, and I have the statement, Jim cooks dinner, and I want what I say to be true unless both of these things are false, what word in the English language do you think I could use to combine them? Frank does the laundry versus Jim cooks dinner. I think that could work. I want to look for a simpler word. Is there something that's more common? Or. Frank does the laundry or Jim cooks dinner. Okay. If they're both false, then my or statement is false. But if Frank does the laundry and Jim does not cook dinner, then what I said is true. And if Jim cooks dinner but Frank does not do the laundry, then this or statement is still true. Okay. Sometimes we might want to add something extra. Frank does the laundry or Jim cooks dinner or both. Okay. All right. So a disjunction we're going to we could refer to as an or statement. Okay. Now, I don't think there are quite as many words that mean or as there are words that mean and. However, or can be a little bit tricky because there are two different things that we mean when we say or in the English language. Okay, so that's what we want to look at here to begin with. We have what we call an exclusive or, and we have what we call an inclusive or. So an exclusive or is when we're using the word or, but we don't mean that both parts can be true. Okay, so for example, your money or your life. We don't mean, both in this case. Okay? What this means is if you if you give me your money, okay, and I still kill you, okay, then you're going to be very angry at me because, it's not that's not what I said, right? Okay. Another example of that is, if I say to my kids, all right, we can either go to Great America or we can go to Disneyland. And they say, yes, we pick both. I'm like, wait, no, that's not what I meant. I meant you can pick one or the other, but not both. Okay. So that's the exclusive or. And I think that's really, really common in the English language, but we can also have something called the inclusive or. And the inclusive or is where we say, okay, the first one or the second one, or we could also have both. So you must take an art class or a humanities class this semester to graduate. Okay. If you take both classes, you'll still graduate. Okay. So when we're talking in English, usually the context is enough for us to know which type of or we mean, which is why it's just one word. Okay. If our language was a little bit more precise, we would have different words for these two things because these really are two different definitions of two different meanings. Okay. All right. When we're working with logic, if I'm writing statements as P and Q and R and so on, I've stripped all the context away. So there's no possible way you can use context to figure out what we mean. So this is not a good system. We have to be very clear about what we mean. So we'll just set that out now. In logic, we will always use an inclusive or. Okay. Now, I'm going to say that we will always use an inclusive or. It's perfectly acceptable to have an exclusive or in logic, but that is a separate thing. Okay, so we don't call that a disjunction and we don't use the same symbol. It's sort of like its own thing. And to help keep down on the confusion, since we're just kind of getting introduced to symbolic logic, and this is just one unit, not a full class, we're going to avoid that other thing. Okay, so we're going to always, in this class, use an inclusive or, right? This is one of the places where your intuition can fail you, because when you're thinking about examples and you're coming up with or statements, oftentimes the things that naturally come to mind are going to be situations where you think of an inclusive or an exclusive or, but what we want when we're using our symbol is an inclusive or. So this is one of the places where we have to be very careful about what our intuition tells us versus what the rules say. Okay, and it's not that your intuition is wrong, it's that we're not comparing like things. Okay, so here we're going to define our disjunction and define the truth table for it. So a disjunction of two statements, okay, we use the upside down of what we use for the and. Okay, this is like a V, okay, instead of a caret, and it's read as P or Q. Okay, This is a statement that's false when both statements are false and true otherwise. Okay, so if I come up with my same truth table as before, as long as either one or both are true, the or statement is true. And the or statement is false only when both statements are false. Okay, so both must be false for the or statement to be false. Okay, so for comparison, for the conjunction, both statements had to be true for the and statement to be true. Okay, so if they're both true, the and statement is true and false otherwise. Okay, here for the disjunction, the or statement, both of them must be false for the or statement to be false, and it's true otherwise. Okay, so they're almost like opposites in that sense. Okay, but we have to be careful. It's not opposites like a negation, and it's not opposites like algebra. So maybe I should not use the word opposites. It's too confusing. It's already been used. Okay. We have another way that we're going to combine things with a conditional statement, and we've already used this a little bit. We just haven't called it a conditional yet. Okay. We're also going to talk about the biconditional, and they sort of go nicely together. Okay. So in order to talk about the conditional, it's probably better to know, or sorry, we'll just go through these one at a time. So when we look at conditional and biconditional, the statements are going to depend on one another. So let's look at the first one, the conditional. When I have two statements P and Q, what we can do is write this as P arrow towards Q, and we read it as if P then Q. Okay. So sometimes we can refer to a conditional statement as an if-then statement. Okay. Here's the way to think about an if-then statement. Okay. There are some cases that I think make sense to everybody, right? When we say if P then Q, and they're both true, then the if-then statement is true. Okay. It's when one or both of them are false that things get confusing. And I think that one of the ways that I like to look at this to help me make sense of it is I like to think of the if-then statement as being like a promise. If you have P, then you're guaranteed Q. Okay. All right. So if you have P and I deliver Q, then I've kept my promise. For example, if I say, if you do all your homework, you'll get an A in the class. Okay. So you do all your homework, you get an A in the class, then I kept my promise. Okay. Let's suppose you do all your homework and you don't get an A in the class, then I didn't keep my promise, so the if-then statement is false. Okay. So if P is true and Q is false, the promise was broken, right? So then the promise is false. Okay, that makes sense. What's confusing is when P is false. So let's suppose I say, if you do your homework, then you will get an A, and you don't do all your homework. Okay. Well, then it doesn't really matter if you get an A or not. We never got a chance to test my promise. Okay. So if it never got a chance to be tested, how do we know if it's true or false? what we do is we just say, okay, we're going to assume that it stays true unless we've proven it false. Okay, so defining it as a promise isn't maybe the best way, but I think it helps, at least in my mind, sort of keep straight what's going on. Okay, let's look at this with a little bit more precise language. When we talk about this, if P then Q, it's not symmetric, right? Like when I have an or statement, Frank does the laundry or Jim cooks dinner. If I were to say Jim cooks dinner or Frank does the laundry, that means the exact same thing. The order doesn't matter. Okay. Same thing with an and statement. Bob read a book and Alice played video games. It means the same thing. Okay. When you flip the order, it doesn't change the meaning of the sentence. Right. For the conditional, the order is important. The first thing guarantees the second, not vice versa. So what we're going to do is we're going to start by having a way to refer to the first part and the second part of the if-then. Okay, so the first part of the if-then we call the antecedent. Okay, we could also say the if part because, you know, remembering antecedent, well, I mean, it's probably just as likely to mix those up as to keep them straight, right? So our goal with introducing the language is to keep things clear so we know what we're referring to. It's not to make things more confusing by adding other words. Okay, so sometimes I'll often just say like the if part to help keep clear what it is, but antecedent is the official term for it. The second statement, Q, is the consequent. Okay, so we'll also have a way to refer to that. We could say like the then part. Okay. So if I think of my example though, if you do all your homework, then you will get an A. You could think of the you will get an A as like a consequence of doing all your homework, right? So consequent hopefully makes some sense here and it's not too bad to remember. But again, we could just say the then part. You're not going to be quizzed on something like antecedent and consequent, right? This is not terms that you have to memorize, that you'll be tested on. It's just stuff to help us understand. Okay, let's look at an example. I'm thinking of a number. If I'm thinking of 6, then I'm thinking of an even number. Okay, so let's pick this apart a little bit. So I can say that I'm thinking of the number 6 is the statement P, and I'm thinking of an even number is the statement Q. So the way that I could symbolize this, right, if I want to take this thing here, then we can symbolize this as if I'm thinking of the number 6, so if P, then Q. Okay, so that's really cutting things down. All right, now we can look at whether or not this is true without knowing what I'm thinking, right? All right, so let's suppose that I'm thinking of the number 6. Well, if I'm thinking of the number 6, then I'm thinking of an even number because 6 is even. Okay. If I'm thinking of some other number, that other number could either be even or odd, right? Okay, so remember the way that we said that a conditional is true, it's really only false if your antecedent, if the if part is true and the then part is false. Okay, the if part is I'm thinking of a number 6. If that's true, then I'm definitely thinking of an even number. Okay, so I can't really have the situation where the if part is true and the then part is false. Okay, so in this case, okay, it is not possible to have a true antecedent, or we could just say if part, right? And a false consequent, okay, or then part. Okay, so the conditional statement, right, which you could also refer to as the if-then statement, is true. Okay, so regardless of what I'm thinking, the if-then statement, right, that conditional statement is a true statement. All right, does that make sense so far? All right. If I haven't confused you yet, then I have one last attempt here. Let's look at the, well, let's look at another example. All right. In English, we don't always say if then in straightforward way. Okay. So, for example, suppose somebody says, if it rains on Saturday, I'll stay home. One would probably expect that if it doesn't rain, okay, then they would go out. All right. So when we say, if it rains on Saturday, I'll stay home, that's not really the same as an if-then statement, okay, because it has another meaning that people probably meant. They probably meant, if it rains on Saturday, I'll stay home, and also, if it doesn't rain on Saturday, I'll go out, okay. So there's something a little extra to that, and what we want to do is make sure that we don't confuse the two. Okay, so this one is actually called a biconditional statement. Okay, so when two statements are combined using a biconditional, then the combined statement is true when both statements have the same truth value. Okay, so we're going to write the biconditional with arrows going both ways, and the way that we read this in logic is P if and only if Q. Okay, so when I look at the truth table, if P and Q are both true, if they match, right, the biconditional is true. If they match being false, the biconditional is true. It's when they don't match that the biconditional is false. Okay, so the biconditional is true when they match, false when they don't match. And when I say match, I mean matching truth values. Okay, in logic, we're going to be more clear than people are in the English language, right? English is a big language. People have lots of colorful ways to express meaning, and that's fine. When we're discussing things in logic, we want to be very clear about our meaning so that we don't make mistakes. So in logic, we're always going to use if-then to refer to a conditional. Okay, and then to refer to a biconditional, okay, we're going to say if and only if. Okay, so remember we had a list of other words that meant the same as the conjunction and. We're not going to do that here. Conditional and biconditional statements are confusing enough, we don't want to look at any other way that we might mean the same thing. Okay. All right. So let's look at an example. Here's a statement. This shape is a triangle if and only if it has 3 sides. So my simple statements, I could start with a statement P, and I'll say this shape is a triangle. And then my other statement Q would be this shape has 3 sides. Okay, so if I wanted to write this in symbols, I could write P double arrow, so P if and only if Q. So I would read this as P if and only if Q. And my symbol here is my arrow pointing both directions. Okay. So we have the conditional statement, if P then Q, right? And you can think of this as being like a promise, right? When you have the P, you're guaranteed Q. If you don't have the P, you don't know what's going on, so we'll just say that the conditional is true by default. The biconditional is saying if you have one, you have the other. Okay, and again, this is symmetric. It doesn't matter. The order doesn't matter. It's just if they both match, you get that they're true. Okay, and when they don't match, biconditional is false. Okay. All right. So that means that when we're looking at the conditional, the order of the statements matters. Okay, so the symbol for the biconditional is this double arrow. Okay. Right. For the conditional, it's just the single arrow, right, pointing from the antecedent to the consequent. Okay. With the biconditional, we don't need to refer to things like antecedent and consequent, okay, because the order doesn't matter, right? So in the conditional statement, we have to be a little bit more careful. The order of the statements matters. Okay. So if P then Q is true, except when Q is false and P is true. Okay. If Q then P is true, except when P is false and Q is true. With a biconditional, the order does not matter. Okay. Either both, when the biconditional is true, that means that both statements are true or both statements are false. Doesn't matter which one comes first. Okay. So let's look at some examples here. I'm going to take 2 simple statements. The statement P, Ellen does the homework in the class. The statement Q, Ellen's final grade will be good. Okay. So what I'm going to do is I'm going to write these. I'm going to go from my symbols back into English sentences. Let's see if I can type these instead. Okay. So when we have this first one, this is if P then Q. So if Ellen does the homework, then her final grade will be good. Okay. When I have the order reversed, if I say if Q then P, what we mean is if Ellen's final grade, I guess we can talk about this in a second. If I wanted to be very strict about things, I would say if Ellen's final grade will be good, then she does the homework. Okay. And that sounds kind of strange. Okay. So when we're writing out our logic sentences back in English, usually what we want to do is sort of, word it so that it doesn't sound so harsh to our ears. Okay. So I could write something like, if Ellen's final grade is good, I could say then she must have done the homework. Or oftentimes when we're saying an if-then statement in English, we leave out the then part. So I'll give you this. I'll use this as an example. If Ellen's final grade is good, she must have done the homework. Okay, we didn't say the then part, but it's kind of implied. Okay, so you can only see the if. And that's actually really common when we're saying or writing things in English, to leave out the then. Okay, now you certainly don't have to. I just want to make that clear. You don't have to see both the if and the then in English for it to be a conditional statement. All right, so let's look at the biconditional statement, P if and only if Q. So if I write that out by just translating directly, right, this will say Ellen does the homework if and only if, extend this a little bit, if and only if her final grade will be good. Okay, and again, if you were to write that sentence, say in a paper, and turn it into your English class, they'd have words for you, right? They'd be like, what are you writing here? Okay, so this sounds a little bit weird. What we want to do is write something that means the same thing, but again, doesn't sound so harsh to our ears. Okay, so I'm just going to change the wording slightly, but keep the same meaning. So something like Ellen's final grade will be good if and only if she does the homework. Okay. Now I switched the order, but that doesn't matter. Okay, it has the same meaning, but I think that it sounds a little bit nicer this way. And also, I mean, that's probably about all we did, but it's still I don't know. It sounds like it makes more sense. Okay, even though it has the same meaning, it just works better as a sentence. Okay, when we use conditionals and biconditionals in English, we tend to assume that one statement causes the other one to be true. Okay, that's not part of formal logic. So we're not talking about cause and effect necessarily. Okay, but I think it's helpful to know how it's actually used in practice. Okay, so that's something that's important to be aware of. Okay, but when we write an if-then statement in logic, we don't mean that there has to be a cause-effect relationship. We're just saying, okay, one follows the other. All right. So what I want to do is take all of the stuff that we just talked about and sort of put it together. Okay. And one of the things that I want to do is make sure that we can translate between English and our logic symbols neatly. Okay. All right. So we're gonna write this stuff down. We're gonna be formal about it, and we want to also we can think about this. The structure of logic is just like our structure for grammar. Okay, so let's be careful about things. Okay, all right. We're gonna pretend we're in English class for a minute. So in grammar, a conjunction is a word that's used to connect words or phrases or clauses. Okay. In logic, we have 4 different things that we have for connecting things together, but only one of them is actually called a conjunction. Okay, so we want to be a little bit, I want to make sure that we mention this, because this is ways in which the way we describe things in logic and the way we describe things in English don't line up perfectly. Okay, so we have to be aware of that. So when we talk about a conjunction, we're talking about the and statement, right? So we have things like P and Q, and our symbol is this, arrow pointing up symbol. Okay. The disjunction is also a way to connect, phrases or clauses. Okay. P or Q, and our symbol for that is the arrow pointing the other way. I think there's like a V. Okay. Our conditional is if P, then Q. When we write that in symbols, right, we use an arrow pointing from P to Q. So this is the only one where our symbol sort of has a direction to it. And again, that makes sense because it's the only one where the order really matters. With the biconditional, we could say P if and only if Q, and we have our double arrow, so again, the order doesn't matter. Okay. So remember, we have other words, especially for and, but it's the same idea. Okay, we still use the same symbol. All right, now we're going to put it all together in a truth table. So I'm going to put all of our, back here, we sort of introduced, or was it? Here's our truth table for a biconditional, a separate truth table for the conditional, right? And the disjunction and the conjunction. And we can put them all together in one single truth table, and it's a little bit more concise. So what we're going to do is we're going to say, all right, I'm going to start with 2 basic statements, statement P, statement Q, and all the possible ways, combinations of them being true and false. So I get my 4 rows. Okay. So if I look at this first row, P is true, Q is true. So then the and statement, I'll just abbreviate this above, right? Or not abbreviate. All right, the and statement is true. The or statement, when they're both true, is true. Okay. The conditional, the if-then statement is true. Okay. And they match, so then the biconditional, if and only if, is true. If P is true and Q is false, I only have one true, they're not both true, so the and statement is false. The or statement, though, is still true. I only need one true for the or statement to be true. Okay. If P, then Q, right, we broke our promise. We had P, but we didn't deliver on Q, so the promise is broken, so that the conditional, the if-then statement is false. For the if and only if, they don't match, so it's false. If we swap the order, false then true, that only makes a difference to the if-then statement. The other ones, it doesn't make a difference to. So the and statement, when one of them is false, the and statement is false, right? When one of them is true, the or statement is true, so it stays true. They don't match here, they don't match here, so the if and only if is the same, right? They don't match, so it's false, okay? But here, if I say if P, then Q, and I don't have P, then we're not breaking our promise, no matter what happens with Q, so the if-then statement is still true. Okay. And finally, when they're both false, the and statement is false, the or statement is false. When they're both false, I don't have the antecedent, right? When we have our if you have P, I promise we'll deliver on Q. If you don't have P, then our promise can't be broken because it wasn't ever tested. Okay. So we say that the promise wasn't broken, it's still true. And then for the if and only if they match, they're both false, that's a match. So the if and only if is true. Okay. So some things that we can notice here. The conjunction, the and statement, is true in one row. The disjunction or statement and the conditional if-then statement are true in 3 rows. Okay. The biconditional is true in 2 rows. We don't have any way to connect statements that are true in 0 rows, because then it wouldn't really be connecting 2 statements. If something was true in 0 rows, if it's always false and it doesn't matter what we started with, we'll have a way to refer to that. Okay, but that's just a statement that's a self-contradiction, right? It's false no matter what happens. Likewise, if we had something that was true in all 4 rows, then it wouldn't really matter what we started with. Okay, so it's not really telling us any way to combine those statements. It's just something that's always true. Okay, and we'll have a way to refer to something like that too later. We'll call that a tautology. But for now, one of the things that we can do is look at how many truths do we get that might help us decide what connector to use. Okay, so let's look at an example. I wanted to go shopping, but the store was closed. Okay, so let's see if we can break this down. We're going to convert this into logical statements. So I'm going to abbreviate I wanted to go shopping with P. Okay. We'll abbreviate the store was closed with Q. Okay. And let's fill in a truth table for the combined statement to see which one it seems like it matches. Okay. So let's look at the statement. I wanted to go shopping, but the store was closed. If I wanted to go shopping and the store was closed, okay, does it seem like this statement was true? I wanted to go shopping, but the store was closed. If it's true that I wanted to go shopping and it's true that the store was closed, then yeah, that seems to line up. Okay. All right. If I say I wanted to go shopping, but the store was closed, and it's true that I wanted to go shopping, but it's not true that the store was closed, that doesn't sound like what I said here, right? Okay. So I wanted to go shopping, but the store was closed doesn't seem to line up with I wanted to go shopping is true, but the store is also open, right? So that doesn't match. It's false. Okay. Let's suppose that P is false. Suppose I didn't want to go shopping. Then that's not what we said here, right? When I say I wanted to go shopping, but the store was closed, okay? If I didn't want to go shopping, then this is not the sentence to use, right? That's not what the sentence is communicating. So when P is false here, I said I wanted to go shopping, okay? If I didn't want to go shopping, that doesn't seem to line up. Okay, so if I'm looking at this statement, I wanted to go shopping, but the store was closed, and I look at its truth table, which connective does that seem to match? Yeah, that looks like, right? True, false, false, false. That looks like P and Q, our conjunction. So this matches the P and Q column in our truth table, and so that's how we can symbolize this statement. All right. Any questions? Feels like that's a lot of information. So what we're going to do is I'm going to leave that for now. That's going to be our introduction to symbolic logic, and we have a lot more, I think, to do with it. Okay, but this is bringing in our connective statements and looking at how do we look at an English sentence, translate it into symbols, and break it down into pieces. Okay, so we're going to stop here for